Welcome to my series on classical thermodynamics. This is lecture number 18. In the last lecture, we met the Legendre transformation. The basic idea behind this transformation was based on geometry. If you are given a function y of x and want to change the independent variable from x to p, which is the derivative of y with respect to x, and this is the critical point, without any loss of information, then merely changing the variable from x to p and rewriting y will not do. What we need to do is consider a transform function, which I have written as y tilde of p here, and which by definition is y minus p times x. Geometrically, the reason behind this was simply that if we know all the tangents to a curve, then we can automatically recover the curve itself, and y minus px happens to be the intercept of a tangent at the point x, y, whose slope is p. Now, one immediate application of that stemmed from the fact that the internal energy expressed in terms of the variables S, V and N, entropy, volume and the number of moles, had complete thermodynamic information about a simple hydrostatic system. When I say simple, I mean that this had only one component. Now, if you want to trade in any one of these variables S, V or N for the corresponding partial derivative, then you would have to take help of the Legendre transformation. And in the previous lecture, we met one such result of a Legendre transformation. We replaced in USVN the variable V and changed it to P, where P, remember, is minus del U del V at constant S and N. So basically is the partial derivative of U with respect to V apart from an unimportant minus sign. So just by following the Legendre transformation formula, which told you that the new function has to be built by subtracting from the old function the variable that you want to get rid of times the derivative that you want to bring in. Here, the variable I want to get rid of from U is V. The derivative happens to be minus P. So we are subtracting minus P times V from U. That is, we are adding PV to U to get this new thermodynamic function, which is called a thermodynamic potential. In fact, U is also called a thermodynamic potential. H is a thermodynamic potential whose arguments could be any set of variables, but when you express it with arguments S, P and N, then the H has exactly the same amount of information, that is complete thermodynamic information, like U expressed as a function of S, V and N. Now, we also saw in the last lecture that for a monoatomic ideal gas, the enthalpy can be given this particular form, written as a function of S, P and N. We had actually derived this from the fundamental equation, the expression of U as a function of S, V and N for a monoatomic ideal gas. Now, in my last lecture, you had a complicated factor here, but it was a constant, so I've just lumped them all together and called this A. This should not be confused by a similar constant A in the expression for U, S, V, N which we had in the last lecture. This constant and that A are related, but they're not equal. That's not really going to make any difference to the rest of my lecture. So I've just simplified the notation by calling this just A. Now I left a challenge at the end of the last lecture for you, the viewers, that was basically the following. Start from the expression for enthalpy given here and using this, figure out the various thermodynamic quantities, which you can figure out by taking derivatives of H with respect to its variables, S, P and N, and using that, try to really recognize this as the monoatomic ideal gas. Now, I am assuming that some of you did not have the time to work this out by the time this video has come in, so I will just quickly show you part at least of the results. Let me remind you, and this is also something that we discussed in the last lecture, that the differential of H, that is differential of U plus PV, is of course du plus PdV plus VdP, and as we had learned in the last couple of lectures actually, that du is given by TdS minus PdV plus mu dN. So when you add PdV plus VdP to this, the PdV part cancels out, and therefore you end up with this expression: dH is TdS plus VdP plus mu dN. And from this expression, you can immediately read off that temperature, volume, and the chemical potential can be figured out as partial derivatives of H with respect to the appropriate variables. For example, if you calculate del H del S, keeping P and N constant, you are definitely going to get T. Because at P and N constant, these two terms are going to drop out, and therefore dH will be simply TdS. Now, if you go back to our expression for the monoatomic ideal gas, the fact that H depends on the entropy through this exponential here, the 2/5 nR sitting in front of S, makes it very easy for us to calculate this derivative. It is simply going to be 2 by 5 nR times H. H, of course, is a function of S, P and N. So this whole expression is a function of S, P and N. But frankly, we don't really need to go any further and substitute this expression here for our purpose right now. Volume, V, will be del H del P, keeping S and N constant. And that immediately can be worked out from this expression to be 2/5 H over P. And now, between these two expressions, it should be very, very easy to eliminate H and see that V is actually given by nRT over P, which gives us the famous equation PV equals nRT, the mechanical equation of state for the ideal gas. Now, of course, from this expression for H, we can also figure out that if we were to partially differentiate H with respect to N, keeping S and P constant, you would get the chemical potential. I will leave that as an exercise for you to work out and show that the expressions that you get here, expressed as functions of S, P and N, are consistent with what you had worked out from the fundamental equation of the monoatomic ideal gas, where U was expressed as a function of S, V and N. I hope that this example has convinced you that the enthalpy expressed as a function of S, P and N has as much thermodynamic information about a given system that U expressed as a function of S, V and N has, and so H expressed as a function of S, P and N has equal right to the name of fundamental equation. Let us now turn to some other features of the quantity that we have just introduced in the last lecture, the enthalpy. Now, if you have ever opened a chemist's thermodynamics book, you will find that enthalpy plays the major role there. For physicists, it's internal energy which is the more common thing to talk about. Enthalpy is more of a sidelight. But in the chemist's book, enthalpy plays a central role. So the question that can naturally arise is, why is enthalpy the chemist's darling? Why do chemists talk about enthalpy all the time in their treatments of thermodynamics? The answer actually follows from the fact that enthalpy is easier to deal with in most chemical situations. To understand why, let us take a look at our formula for du. This is basically the first law of thermodynamics. And we are looking at a closed system, so du involves just d cross q minus p dv. There is no mu dn term here. Now at constant volume, of course, du is the same as d cross q. I'm of course talking only about hydrostatic systems for the time being. Now when you look at d cross q and integrate that, you get the net amount of heat absorbed by a system at constant volume is equal to the increase in its internal energy. This of course has an immediate consequence that if we were to partially differentiate u with respect to temperature, holding the volume fixed, you will get heat capacity at constant volume. Remember, this is u which you are differentiating, but du is the same as d cross q. So this is essentially the amount of heat absorbed per unit temperature rise for a situation where the volume is constant. Now this actually is what the physicist focuses upon. And the reason why physicists focus on this is that the volume being fixed means the boundaries of the system is fixed. And boundaries being fixed means you can, if you wanted to look at the thing microscopically, deal with standard fixed boundary conditions, and that makes calculations from the microscopic point of view a lot easier. On the other hand, if you look at the expression for H, U plus PV, and looked at dH, which by a very similar calculation that we had done a while ago, will simply turn out to be d cross q plus VdP. The minus PdV and the plus PdV from the d of PV would simply cancel. And now notice that when pressure is held constant, dH is the same as d cross q, and for a process carried out at constant pressure, q, the integral of d cross q, would turn out to be delta H. So H is related to the heat absorbed by a system. Indeed, increase of H is exactly equal to the heat absorbed by a system at constant pressure. Of course, if the enthalpy were to decrease in a process, that would mean that the heat would be released, at least if the process were being carried out at constant pressure. And again, immediate consequence, Cp, which is d cross q dt at constant pressure, is the same as the partial derivative of H with respect to temperature at constant pressure. Note that we are not mentioning constant n here in these expressions for both Cv and Cp because that's sort of a given. We are talking only about closed systems. Now here comes the main point. Chemists are actually way more practical people than physicists. At least, let's be nice to chemists for a while. It's way simpler to carry out chemical reactions at constant pressure. For example, at a pressure of 1 atmosphere, than at constant volume. Constant volume would require you to have a container which does not expand or contract as the reaction is taking place, but that would actually put huge amount of mechanical stress on the material of that container, and frankly, all containers do expand or shrink as the temperature of the substances inside would change because of the chemical reaction taking place. So since it's much easier to work at constant pressure than at constant volume, a chemist typically prefers something which would essentially tell you heat absorbed at constant pressure rather than heat absorbed at constant volume, which is why enthalpy reigns supreme in the chemist's world. And the increase in H is often called the heat of reaction. Very often it's the decrease of H which is really called the heat of reaction, because when H decreases, heat is released. You have an exothermic chemical reaction. Let us now turn to the question of some properties of the enthalpy. We have seen in a previous lecture that U, because of extensivity and because it's a function of three extensive variables, obeys the Gibbs-Duhem relation. U is equal to Ts minus Pv plus mu n. Now, this immediately tells you that H, the enthalpy, which is U plus PV, has to be given by Ts plus mu n. This is another example of Gibbs-Duhem relation, this time talking about enthalpy in terms of the variables involved, the extensive and intensive variables that describe the state of the system. Now we can derive this expression ab initio as well. Notice that H, which is expressed as a function of S, P and N, is an extensive function, but the variables involved here, two of them, S and N, are extensive, and the other, P, is an intensive variable. As a result, when you scale up a system by a factor lambda, its enthalpy must scale up by the same factor, but the arguments which go into the function for enthalpy do not all scale up. S scales up by a factor of lambda, so does N, but P stays P. So H of lambda S, P, lambda N is lambda times H of S, P, N. This is just the extensivity of H that is being used here. Now, if you start with this expression and follow exactly the same steps that led us to the Gibbs-Duhem relation U equals Ts minus PV plus mu n, that is to say, you differentiate both sides of the equation with respect to lambda and then put lambda equal to 1, you will immediately end up with S from this variable, the first variable here, times del H del S at P, N, plus N from the third argument times del H del N S, P is equal to H S P N, which is just what you get when you differentiate this side with respect to lambda. And recognizing that del H del S at constant P, N and del H del N at constant S, P are T and mu respectively, you end up with H equals Ts plus mu n. We will come back to discuss other features of the enthalpy later on. There will be several situations where enthalpy will be important as a physical quantity. But for the time being, let us focus on the question of doing a Legendre transformation on U while maintaining complete information. Now what we have seen is if you were to swap out volume and bring in pressure, you end up with this quantity called the enthalpy. But why stop at only that? We can swap out S from U of SVN and bring in T, which is the temperature, the partial derivative of U with respect to S at constant VNN. But if you do that, you have to change the function U if you want to retain complete thermodynamic information. You have to change it to U minus the product of T and S. Remember once again, Legendre transformation involves subtracting from the function, in this case U, the product of the variable you are swapping out with the variable, the derivative that you are swapping in. This quantity U minus Ts happens to be a very important quantity in statistical mechanics and thermodynamics. It's called the Helmholtz free energy, F, and its natural arguments, or rather the arguments which help it retain complete information, are T, V and N. Well, we can immediately write down the Gibbs-Duhem version for this. After all, remember U was Ts minus PV plus mu n. Subtracting Ts from that immediately gives us F is minus PV plus mu n. This can also be directly figured out, and I will leave that as an exercise for you, from the fact that among the arguments of F, V and N are extensive and T is intensive, and F of course is itself an extensive variable. We can also swap out both S and V and bring in their places respectively T and P. You don't have to swap out one variable at a time, you can do both. And for this, we have to define a new function. Again, all these functions are called thermodynamic potentials. A new thermodynamic potential called the Gibbs potential. And the Gibbs potential is obtained from U by subtracting Ts and adding PV. Remember, adding PV is actually subtracting minus P times V. Now when you do both of these, subtract Ts and add PV, you end up with a new thermodynamic potential which has complete information about the system, provided you express it as functions of temperature, pressure and number of moles. Now, among the arguments of G, only N is extensive, the rest are all intensive. There are other ways of expressing this of course. U plus PV being H means you can write this as H minus Ts. You can also write this as F, as we have just seen. So this is F plus PV as well. So these are all alternate ways of writing down Gibbs potential or the Gibbs free energy. Now why is this called Gibbs free energy? Why is Helmholtz free energy called Helmholtz free energy? Apart from the fact that they are named after two people, why they are called free energy is a topic that we are going to return to in a later lecture. For the time being, let's point out that from Gibbs to Hem, we can immediately figure out that G of Tpn is simply mu times n. That's the only thing that survives after you subtract Ts and add Pv. You could of course have worked it out directly by noticing that G is an extensive function of two intensive and one extensive variable and repeating the same steps that led to the original Gibbs-Duhem relation. But this has one important sidelight. This tells us that the chemical potential mu, the new thing that we met in a recent lecture, is actually nothing but Gibbs free energy per mole. This is going to be critically important later on when we talk about things like phase transitions or chemical reactions. Now each of these thermodynamic potentials, as we have said, U S V n, H as a function of Sp and n, F as a function of Tv and n, and G as a function of Tp and n, have complete thermodynamic information. Since we are meeting the free energies for the first time, let me illustrate how at least one of them does furnish complete thermodynamic information. We will do this for the Helmholtz free energy F. You can do something very similar for the Gibbs free energy G, which I will leave you to worry about. Now, with F, you start from its definition that F is U minus Ts, and this immediately tells us that the differential of F is du minus Tds minus Sdt. Now, if we replace du by the expression Tds minus Pdv plus mu dn and subtract from it Tds and Sdt, it's easy to see that the two Tds's cancel out and you are left with minus Sdt minus Pdv plus mu dn. And from here, it's obvious that you can find out S, P and mu by carrying out appropriate partial derivatives. Del F del T at constant V and N would simply be minus S. Similarly, P can be immediately read off from this expression to be minus del F del V at constant T and N, and mu, the chemical potential, is del F del N at constant temperature and volume. Just to illustrate how these could be used to extract complete thermodynamic information, let us go back to our favorite old example. You have the internal energy of monoatomic ideal gas given by this expression. What you need to do, of course, is to calculate the free energy from here. The first step would be to figure out what temperature is as a function of S, V and N. Now, that is a pretty straightforward thing. That is something we have already done before. It's 2 by 3 Nr times U. And since we want to figure out S from here, we have to replace the U by this whole expression. And that's what this will come out to be. Just a quick check. This is an intensive variable as temperature should be. Scaling up the system would change N and V both by factors of lambda, which will cancel here. As well as S and N also will pick up factors of lambda that will also cancel here. So T will stay T when you scale up the system. as it should. Now, you can immediately solve this for entropy, but we will really need 2s by 3nr. So let's just figure that out. You move this entire thing to the other side to read exponential of 2s by 3nr is 3rt by 2a times n by v to the power minus 2/3. And take the log of both sides to get 2s by 3nr is log to the base e, of course, natural logarithm of 3rt by 2a minus 2/3 log of n by v. Now this immediately tells us that the free energy F, which is U minus Ts, can be written down as U minus 2 by 3 nr times U times S. So we have taken the U common here. And 2s by 3 nr is this quantity which we need to now substitute. So we get F is U into 1 minus this whole thing. But we also need to remember to rewrite U as a function of N, T and V. And we already know that that is 3 by 2 nRT. Something which we had figured out earlier as well as something which we could figure out simply from this expression that U is 3 by 2 nRT. Now that together gives us the Helmholtz free energy F as a function of temperature, number of moles and the volume here. Now to show that this will give you the complete thermodynamic information will take some time. So I will just quickly show you one result which will help you recognize the monoatomic ideal gas once again. You just calculate pressure from here. All you have to do is take the partial derivative of the free energy with respect to the volume, keeping T and N fixed and put in a minus sign. So calculating that will simply give you minus 3 by 2 nRT from this factor, which will be treated as a constant for this partial derivative, times the derivative of this, and nothing here contributes. Only this term does, and that gives you minus 2/3 into 1 over V. And after calculations, you can immediately see that this is the same as nRT over V. So we are getting back PV equal to nRT, the familiar equation for an ideal gas. I will let you figure out that if you were to try to calculate the entropy from this or the chemical potential, you will get results which are consistent with what you have found out earlier. Of course, the expressions for entropy and mu may be new, but you will be able to re-express them in terms of the old variables that you have used for, say, the internal energy case and check that you actually have the same expressions. Now, while you are at it, why don't you try to do the same thing with Gibbs free energy? Of course, you have to first figure out the appropriate partial derivatives to take, and that is pretty straightforward. Starting from G equals U minus Ts plus PV, you should be able to immediately show that dG is minus SDT plus VdP plus mu dN. And then it's child's play to read off the partial derivatives that you need to take. If you differentiate with respect to the temperature, keeping P and N fixed, you're going to get minus S. So S equals minus del G del T at constant P and N. Volume is plus del G del P at constant T and N. And mu, once again, is a partial derivative with respect to N. But this time it's a partial derivative of the Gibbs free energy with respect to N, with temperature and pressure held constant. Now, so far we have talked about getting rid of either S or V or both and bringing in their corresponding derivatives. Other potentials could also be written down. Potentials with arguments like SV mu, where you have traded the N for mu, or TV mu, where you have traded both S and N for T and mu respectively. These are less commonly used. I must stress though that if you are studying statistical mechanics, especially statistical mechanics of the grand canonical ensemble, you will get something called the grand canonical partition function, which leads to a potential whose arguments are really TV and mu. So while these possibilities are less common, you can definitely have that. But one thing could strike us. You started with internal energy expressed as a function of S, V and N. And what we have done so far is traded in one or more of these arguments for the corresponding derivatives. Can't we do all of this at one go? That is, can't we get rid of S, V, N, all of them, and bring in T, P and mu, the corresponding partial derivatives of U? Now, even before we try our hand at this, you should realize that this is a bad idea. After all these thermodynamic potentials that we have seen so far are basically extensive variables. You can of course check that if you start with U and take away PV, you are starting with an extensive variable, and the product PV that you are taking out is of an intensive variable P and an extensive one V. So the overall thing is extensive. So the whole thing is an extensive variable. And that is true for all of these thermodynamic potentials that we have got so far. So the thermodynamic potential we expect here would be extensive. However, it is now written as a function of temperature, pressure and chemical potential, each of which are intensive variables. So how can an extensive variable be a function of only intensive variables? After all, if this were true, then this potential capital theta of Tp mu would have to obey a relation like this. That is, if you would scale up the system, temperature, pressure or mu will not change. So they will say Tp mu on both sides, but the overall thing must get multiplied by lambda, the scaling factor. And the only theta that actually is consistent with this is theta of 0, which of course has no information whatsoever. And that's easy also to see from the Gibbs-Duhem relation. If you want to swap out S, V and N and bring in T, P and mu, that is carry out 3 Legendre transformations simultaneously, then you have to subtract from U Ts minus PV and mu n. That is, this new potential, capital theta, would have to be U minus Ts plus PV minus mu n. However, the Gibbs-Duhem relation tells us that this must vanish identically. So you cannot really go the whole hog. You cannot get rid of all the extensive variables at the same time and still retain information. That's all for today's lecture. At least that's all the thermodynamics that we have for today's lecture. Before I go, however, let me make a brief foray into a slightly different topic, where the Legendre transformation also plays a very important role. This is dynamics. Now, those of you who have met classical dynamics before would of course know what I am talking about. Those of you who haven't can perhaps skip this part. Anyway, just for completeness, let me just mention this, that the dynamics of a system is completely described by a function of its generalized coordinates and generalized velocities. Q1, Q2 up to Qn are generalized coordinates, and those with the dots here are time derivatives of those quantities, q dot 1, q dot 2 up to q dot n. These are the generalized velocities. And possibly t. Now this function, which controls all the dynamics of the system, is called the Lagrangian, L, which is a function, as I mentioned, of q1 through qn and q dot 1 through q dot n and t. Let me point out that the 1, 2 here are not powers, despite being written as superfixes. These are just indices. Why are they written as superfixes is a different story. I will not go into that right now. Now, the derivatives of L with respect to the q dot i's, the velocities, are called the generalized momenta. So pi, this time with a suffix, is defined to be del L del q dot I. So here we have a bunch of variables and a function written in terms of those variables which actually has complete information about the dynamics. What we have here are derivatives of that function with respect to some of these variables, the velocities. Swapping out the velocities and bringing in the corresponding derivatives, so getting rid of the q dot i's and bringing in the pi's, while retaining complete dynamical information, can be done via a series of Legendre transformations. Not really one, but a sequence of them. You get rid of each one of them one at a time, or maybe do them all at one go. And that would involve taking away from L, the original function, the product of the variable you want to get rid of, that is q dot I, times the derivative that you are swapping in, pi. So q dot 1 p1, q dot 2 p2, all the way up to q dot n pn has to be taken away from L in order to get a function which, when expressed in terms of the q's, which we have not touched, and the p's instead of q dots, and t, will have complete dynamical information. This actually is what we call the Hamiltonian. Apart from a trivial matter of a sign, the Hamiltonian H describing the dynamics of the system, which has all the information about the dynamics of the system, is a function of q1 through qn, and instead of the q dots you have p1 through pn here and t, and it is defined to be the negative of this quantity, sum from I equals 1 to n, pi qi dot minus L. Now I will not go any further into this topic because that will lead us too far afield. Dynamics is another very important place where the Legendre transformation plays a very important role, and I just wanted to emphasize that in the last part of this video. We will return with a lot more details about the thermodynamic potentials that we have met in this particular lecture. In the next lecture, we will return with a lot more details about the various thermodynamic potentials that we have met in this lecture, their applications, their physical significance, and so on. Bye till then.